All right, we're gonna continue on doing some homework problems out of the textbook. So we're on number 54. All right, so number 54 gives us a base, NH2OH, and a 0.21 molar of the base. And you look up the Kb, and it is 1.1 times 10 to the minus 8. All right, and so we have a base, so we're going to write the Kb reaction. All right, so you can do generic Kb reaction, A minus plus H2O goes to your HA plus OH minus. If you want the specific Kb reaction, you have your NH2OH plus H2O, and that goes to NHOH. It goes to NH3OH plus and OH minus. All right, so just like you have your acid and base conjugates here. All right, so there's your base, there's the conjugate acid, one more H. Again here, this is your base, there's your conjugate acid. All right, so you can label those. This is your base, that's your weak base, that's why you're writing a Kb reaction. And this is your acid, and they are conjugates because they differ by one H plus. OH minus is, of course, the base. The conjugate acid is H2O because it has one more H than the OH minus. All right, so again, you can write a generic, you can write a specific. It doesn't matter. What you have is you have your initial of 0.21 molar. Water is a liquid. It doesn't go into your equilibrium setup. And this is the Kb reaction with the Kb constant given as 1.1 times 10 to the minus 8. And to double check, to make sure you don't have to check your X value, you take your concentration of your base divided by your Kb and see if it is greater than 1,000. And when you take your 0.21 divided by your 1.1 times 10 to the minus 8, it is a giant number. It is 1.9 times 10 to the 7th, or some giant number. I'm not going to count how many decimals are on my calculator. It's way more than 1,000. All right, and so when we go to our change, you can't have zeros, so minus x plus x plus x. Then at equilibrium, you have your 0.21 minus x, x, and x. And so when we have our x squared over 0.21 minus x, we neglect the x, and that is our answer because our CB over our KB was much greater than 1,000. So your x squared divided by your 0.21 minus x equals 1.1 times 10 to the minus 8. So you neglect your x, you do not have to check it. So 1.1 times 10 to the minus 8 times 0.21. And then you take the square root of that, and you get a 4.81 times 10 to the minus 5. Or just 2 sig figs is all we need, 4.8 times 10 to the minus 5. All right, so again, you always have to look and see what x is. In this case, it's the Kb, so x is equal to your OH minus concentration. And so we can go to the POH. So the negative log of that. And we get a 4.32. All right, of course, it asks for the pH, not the POH, and so the pH is 9.68. Because your pH plus your POH has to equal 14. And 4.32 and 9.68 give you 14. All right, so that was number 54. Oh, it asks for the concentration of hydroxide ion. All right, so you want to put your units in. And so your hydroxide ion is 4.8 times 10 to the minus 5. That was your X value. of course, your concentrations are in molarity. So, all right, and the next question has an error in it, which is 16.60. All right, and so in this case, it just wants to know if this salt is an acid, a base, or neutral salt. All right, so A is Na2S. All right, and so so you look at the base from the cation. Since NaOH is a strong base, all right, so that means that the Na, well, it's always a spectator ion. It never has anything to do with the pH. And so there is zero effect on the Na. So anytime you have sodium, it doesn't have any effect on your acid-base properties. It's always neutral. Now we're looking at S minus 2. We look at the conjugate acid. So you can look at the conjugate acid, HS minus. That is not a memorized strong acid, and neither is the H2S, the one where it's differing by 2 H pluses. All right, and so since this is a weak acid and not a strong acid, remember the conjugate of a weak, the weaker acid has a stronger conjugate base. And so this is actually basic. And so since sodium has no effect on the pH and S minus 2 is basic, well, then this is going to be a pH greater than 7. So this is going to be a basic solution. So if you take water and you dissolve sodium sulfide and you take the pH is greater than 7. Part B is the one that has the error. What it's supposed to say, what it doesn't say, what it's supposed to say is CuNO3 sub 2. They got happy with their 2's and they made it NO2 sub 2. And if it's NO2 sub 2 and it's copper, then your answer is not enough information to determine that answer. All right, so it is not NO2, it is NO3 in the problem. Should be in the problem, it's just a typo. What we do know is NO3 minus is the conjugate of a strong acid. This is the conjugate of HNO3, which is one of your 6 memorized strong acids. And so this is extremely weak. So weak, it has zero effect on your pH. So NO3 minus has no effect on pH. All right, now if we look at copper hydroxide, CuOH2 or 1, it can be copper 1, it can be copper, well, this one's copper 2. So it is in CuOH2, all right? That is not one of your 6 memorized strong bases. All right, and so this has an acid effect, and so this is acidic. All right. If we look at part C, if this was kept at NO2, then HNO2 is not a strong acid, it's a weak acid, so that would make it basic. The copper would make it acidic, and you wouldn't know which way to go. There would be not enough information to determine the actual problem in the book, which is a typo. KNO3, when we do KNO3, all salts of potassium are soluble. KOH is a strong base. All right, and so K, just like sodium, has zero effect on pH. All right, and then we just did the NO3 minus. This is the conjugate of a strong acid. It has zero effect on the pH. This one is neutral. And then part D. All right, so part D is an interesting one. You've got CH3, NH3 plus. That would be the plus, and then the Cl minus. So that is your ammonium salt. All right, so this is methyl ammonium chloride. All right, so all ammonium salts that have an NEH here, this has 3 H's, and a plus, this is always an acid. All right, so NH3 CH3NH3OH is not a strong base. It's not one of the 6 strong bases. And we see that the Cl minus is the conjugate of a strong acid. HCl, of course, is a strong acid. So the conjugate base has 0 effect on the pH. All right, and so this again is going to be acidic. All right, so you'll be given salts and you're going to add water to it, and you have to predict whether the pH is going to go up if it's a base or if it's going to go down, which is an acid. All right, so that is number 60. 66. Calculate the OH minus concentration and pH of a 0.0025 molar aqueous solution of sodium cyanide. Again, sodium has 0 effect on anything, so that is Cn minus. So sodium has no effect, Cn minus. We know that HCN is not one of the 6 strong acids. This is going to be basic. All right, so we know that the pH of that is going to be greater than 7. And then it also wants the concentration of everything. So it also wants the hydronium ion, which is, of course, the H3O plus, which is the same as your H plus. So we need the concentration. Find the concentration there. We need to find the concentration of the Cn minus, and we need to find the concentration of your HCN. So it wants all concentrations, and it wants the pH of 0.0025 molar NaCN. All right, and so we look up the Cn minus, look for a Kb. There's not one there, but we look at the HA chart, Ka chart, and we find your HCN has a Ka value of 4.9 times 10 to the minus 10. So there is not a Kb, but there is a Ka, and so we have to be able to take our Ka times our Kb and get Kw. So we have to solve for Kb. So that is your Kw, 1 times 10 to the minus 14, divided by your Ka, 4.9 times 10 to the minus 10. So when you take your 1 times 10 to the minus 14 and you divide your 4.9 times 10 to the minus 10, you get a 2.0 times 10 to the minus 5. All right, so now we need to find out if this is going to be an easy question or a hard question. Well, it depends on what your definition is, but for me, if I don't have to check my X, I feel like that's an easy question. In order to not check your X, your concentration of your base divided by your Kb has to be greater than 1,000. So we do our concentration of base. Unfortunately, it is very small, 0.0025, divided by the 2.0 times 10 to the minus 5. So when you take your 0.0025 and divide by your 2.0 times 10 to the minus 5, you get 125, not the answer you're looking for. All right, so it is not greater than 1,000, which means you have to do either the quadratic equation or successive approximations. And as usual, I will do the successive approximations. All right, so I have my Cn minus, or if you want to do generic, A minus plus H2O goes to my HCN and my OH minus. The initial concentration of the Cn minus is 0.0025. Water's a liquid, and then this is 0, so it has to go to the right. And then at equilibrium, we have a 0.0025 minus X. We have X, and we have X. And so when we plug it into the Kb, we've got x times x, which is x squared, divided by 0.0025 minus x is equal to the 2.0 times 10 to the minus 5. All right, and so again, we are going to get our x values. The concentration divided by the KB was not greater than 1,000. And so we're going to neglect our x and take our 2 times 10 to the minus 5, multiply by 0.0025, get the square root of that for x1, and that is 2.2 times 10 to the minus 4. So we plug that in, and we get our x2. So we have 0.0025 minus that answer times 2 times 10 to the minus 5, and then the square root of that. And our second answer is 2.1 times 10 to the minus 4. So it is very helpful to only have 2 sig figs. So it's between 2.2 and 2.1, so we plug that in. So 0.0025 minus that answer times 2 times 10 to the minus 5, and then the square root of that. And again, 2.1 times 10 to the minus 4. All right, so our x value is 2.1 times 10 to the minus 4, and we see that our equation, that is our concentration of OH minus. So the OH minus concentration is 2.1 times 10 to the minus 4 molar. And from that, we can get our POH, which is the negative log of the 2.1 times 10 to the minus 4. Which is a 3.68. All right, did not ask for the POH, it asked for the pH, which is a 10.32. All right, so it also asks for all of your concentrations, so not just the OH minus. All right, so we want the H plus. You can do it one of two ways. I can convert my pH to the concentration of H plus. All right, I take the negative of both sides, and then I take my inverse log. Inverse log is your 10 to the x. So I get that by taking 10 to the negative 10.32. 4.8 times 10 to the minus 11. All right, and remember that your H plus times your OH minus always equals KW. So when you multiply your 2.1 times 10 to the minus 4 times 4.8 times 10 to the minus 11, that's going to give you 1 times 10 to the minus 14. And then we have our concentration of our CN minus. The CN minus concentration, as we see right up here, is the 0.0025 minus the X value. So the CN minus concentration is 0.0025 minus the X value of 2.1 times 10 to the minus 4, and that gives you a 0.0023. And then your OH minus is the X value that is also equal to your HCN concentration, because they are both equal to X. So if you scroll back up here and you see that your HCN and your OH minus, they are both your OH minus and your HCN are equal to the X value. All right, and so that answers all the questions that is asked on that one. It wanted all the concentrations and it wanted the pH. All right, number 70. Calculate degree of ionization of 0.22 molar of formic acid. All right, so 0.22 molar formic acid. Again, I'm just going to do generic. All right, the same solution that is also, okay, so we're going to do it twice. So 0.22 molar HA by itself. And so then like part B, 0.22 molar HA with 0.15 molar HCl. And the Ka value for formic acid, you find it on a table. The Ka for formic acid, 1.7 times 10 to the minus 4. All right, so we have our HA, formic acid, going to H plus and A minus. All right, and so we just have our 0.22 molar. So change minus x plus x equilibrium. You have your 0.22 minus x, you have x, you have x. All right, so you have your x squared over 0.22 minus x is equal to the Ka 1.7 times 10 to the minus 4. So again, be aware of the reaction that you're writing. This is the Ka, and so it's equal to the Ka. Again, we have to see if we have to check our x value or not. So you got to take your Ca divided by your Ka and see if that is greater than 1,000. So we take our numbers, 0.22 divided by 1.7 times 10 to the minus 4. And when we take 0.22 and divide by 1.7 times 10 to the minus 4, we get 1,300. So we are happy about that. Barely greater than 1,000, but greater than 1,000, which means that we can just take our x1 value and go with it. So we can neglect that. We do not have to check that answer. So 1.7 times 10 to the minus 4 times 0.22, and the square root of that, 0.0061. So your x is 0.0061. All right. So I'll answer more questions than they're asking here. X is my concentration of H plus. So I can go to the pH of this. So the negative log of that, they didn't ask for this, but 2.21. So the pH is a 2.21. What they asked for was the degree of ionization. And so that's X over your initial concentration. So your X value, 0.0061. Your initial concentration was 0.22. And your degree of ionization is a 0.028. Or if you wanted to do percent, or 2.8%. But the degree of ionization was the question, 0.028. All right, so now it says we're going to add 0.15 molar HCl. What you need to know is HCl is a strong acid, and so that is 0.15 molar of H plus. And so the difference here, we have the same reaction, except our initial concentration of H plus is not 0. So we still have the same reaction, the same Ka, your formic acid, H plus, your A minus. We still have the 0.22 molar, but this time we added 0.15 molar of HCl. And this is 0. Here we don't have to check to see if we can go with X1 as our answer. We know that we have an initial concentration of both a reactant and a product. We never have to check our X value. And so we can't have a 0, so we know it has to go to the right. So at equilibrium, we have 0.22 minus x, we have 0.15 plus x, we have x. So we have x, and then we have 0.15 plus x, over 0.22 minus x, and we are going to neglect our plus and minus x. We do not have to check it, and that is equal to the Ka, which is 1.7 times 10 to the minus 4. So we take our 1.7 times 10 to the minus 4, multiply it by 0.22, divide it by 0.15, and we get 2.5 times 10 to the minus 4. All right, so a trick question here would be calculate the pH. And so people will take the negative log of 2.5 times 10 to the minus 4 because x, this is the Ka, so x is, of course, H plus. X is not equal to H plus. H plus is equal to 0.15 plus the 2.5 times 10 to the minus 4, which is equal to 0.15. Your x value is so small. Remember, when you have an initial concentration of a reactant and a product, your equilibrium concentration is exactly the same as it was in the initial. The amount that it changes is so small, it will not change that value. And so to get the pH, it's simply the negative log of 0.15, which is a pH of 0.82. All right, so that would be a trick question. What is the pH? It's actually a simple question, but people will get it wrong because they'll say X, this is Ka, X is my H plus. It is not. The H plus is 0.15 plus this X value, which is so small, it doesn't change the initial concentration. But the problem here asks for the degree of ionization. So we simply take our X divided by our initial concentration. So 2.5 times 10 to the minus 4 divided by 0.22. And that gives us a degree of ionization of 0.0011, or as a percent, that's what they wanted a degree. If you were doing a percent, it is 0.11%. So it went from a 2.8% to a 0.11% because we added a product. When you add a product, Le Chatelier's principle, you shift the equilibrium to the left. So that means less is going to come to the right. Can't have a zero, so some is going to come to the right, but less is going to come to the right because we added a product. All right, so that was number 72. 72, what is the pH of a solution that is 0.2 molar of KOCN? Now, this is where you have to be careful because we have KOCN and we have HOCN. The previous question is different. It was CN minus and HCN. All right, so HOCN is a completely different acid than HCN. All right, so what is the pH solution that has 0.2 molar in the KOCN and 0.1 molar in the HOCN? All right, so this has a Ka. When we look up this in the chart, there's no Kb for the OCN minus, but there is a Ka for the HOCN. That is the 3.5 times 10 to the minus 4. So make sure you're using that and not the Ka for the HCN. This is not HCN, this is HOCN. All right, so I immediately see that the potassium is always a spectator ion, and so I have my weak base and its conjugate, weak acid, in some non-zero concentrations, 0.2, 0.1, and there's no H plus, there's no OH minus. So I say I have a buffer. If you recognize this as a buffer, I think that's easier, but you can write the Ka or the Kb reaction, either one. and get your answer. But if you recognize this as a buffer, then you just go right to pH is equal to the pKa plus the log of A minus over HA. All right, so there's the Ka. So you get the pKa by taking the negative log of 3.5 times 10 to the minus 4. So the negative log of 3.5 times 10 to the minus 4 is 3.46. And so I have the pH is equal to 3.46 plus the log of your A minus, your OCN minus is your A minus, 0.20 molar, over your HA, which is your HOCN, which is your 0.10 molar. All right, so you have your 3.46 plus the log of 0.2 divided by 0.1, and you get a pH. And so since we have a higher concentration of our base, 0.2, than our acid, 0.1, it is going to have a pH higher than 3.46, and it is a 3.76. All right, and so this would be a good buffer to buffer right at the pKa. So if you wanted something to have a pH very close to 3.46 and stay relatively close to that, this would be a good buffer system. Remember the pKa, that is where your buffer would be a good pH for. So in this case, your pKa 3.46, it would buffer it very near there. So even though we had twice as much of our base as our acid, we are just then slightly above that at 3.76 as our pH. All right, 16.74. What is the pH of a solution? That is 0.15 molar of C2H5NH2, which is ethylene or ethylamine. All right, so that is a base. So 0.15 molar of my A minus, or you can write out the ethylene diamine, and 0.10 molar of my ethyl ammonium bromide. So that is, when you look at the difference there, that is the H plus difference. So here is very similar to our NH3 and our NH4 plus. All right, and so it's just having an ethyl group there instead of a hydrogen. All right, and so instead of NH3, they put in a CH2, CH3, CH2 with an NH2. So they took out one of the H's and put CH2, CH3. And then here you have your CH3, CH2, NH3 plus, and your Br minus. And since bromine is the conjugate of a strong acid, the Br minus has nothing to do with this problem. All right, so you should recognize that you have a base and you have its conjugate acid. So here you have a buffer. All right, and so when you look this up, you do not see any Ka for that acid, but for this base, you get the Kb for ethylamine, and that is 4.7 times 10 to the minus 4. All right, and so if you know that you have A minus and HA, no H plus, no OH minus, then you have a buffer. So to find the pH, pH is equal to the pKa plus the log of A minus over HA. Except this time we don't have the Kb, or the Ka, we have the Kb. So you have to always know that your Ka times your Kb is equal to your Kw. We need to solve for Ka, which is your Kw divided by your Kb. So when you take 1 times 10 to the minus 14 and divide by the 4.7 times 10 to the minus 4, you have the Ka. And so your Ka is 2.1 times 10 to the minus 11, but we want the pKa, so we need to take the negative log of that. So when you take the negative log of that answer, you get a 10.67. All right, and so your pH is equal to your pKa, 10.67, plus the log of the concentration of the base, 0.15, the weak base, divided by the concentration of the weak acid, 0.10. And that gives you a 10.85. All right, so we had more of the base, 0.15 molar, more base than we had acid. All right, and so we knew that our pH would go up from the 10.67, but only slightly because we have a buffer. All right, so this would be a great buffer if you needed something to be buffered at the 10.67 pH. Okay, 76. All right, a buffer. So this one tells you that it's a buffer, except, yeah, this one is where you have volumes. And when you have volumes, you have a lot more work to do. All right, so we added 115 mils of 0.3 molar NH3 to 135 mils of 0.15 molar NH4NO3. All right, so that is NH4 plus. When you have NH4NO3, you have to recognize that your NO3 minus is the conjugate of HNO3, which is a strong acid, which has zero effect on your pH. And so that is simply NH4 plus. So it doesn't matter. In the previous one, they used Br. If you have NH4Br, again, the Br is the conjugate of a strong acid. Prior to that, we had NH4Cl. HCl is a strong acid, so that makes no difference. And this time they use an NH4NO3. HNO3 is the conjugate of a strong acid. All of these things would be exactly the same. All right, so we're making a buffer. All right, and so we added 115 mils of 0.3 molar NH3 to 135 mils of 0.15 molar NH4 plus. So we're doing MV is equal to MV. But the final volume, when you add 115 to 135, is 250 mils. So we have to find the molarity when we have 250 mils added. Here we have to find the molarity once we know that the total volume at the end is 250 milliliters. So you take your 115 times your 0.3 and divide by your 250. So we end up with an NH3 concentration of 0.138. We end up with an NH4 plus concentration when we take our 135 times the 0.15 and divide that by the 250 of 0.081. All right, and so it even says in the problem that this is a buffer. All right, so again, you have the base with its conjugate acid that are non-zero concentrations, no H plus, no OH minus, you have a buffer. And so the pH is equal to the pKa plus the log of A minus over HA. All right, we look up the Kas. They are not there for NH3. However, we look at NH3 and it has a Kb. So in the Kb chart, it is 1.8 times 10 to the minus 5. So the same thing that we did in the last problem. We don't want the KB, we want the KA. But we know that KA times KB is equal to KW. So to find your KA, you take your KW, divide by the KB. We take 1 times 10 to the minus 14 and divide by 1.8 times 10 to the minus 5. And we get 5.6 times 10 to the minus 10. So the KA is 5 repeating times 10 to the minus 10. If you round that to 5.6 and clear out your calculator fine, I'm going to leave the repeating 5 in there, and I'm going to take the negative log of that answer and get a 9.26. All right, so your pKa is 9.26. If you round it to a 5.6, your answer is going to be 9.25, and that is fine. All right, so the pH is equal to the 9.26. I didn't round it until then. Plus the log of the A minus concentration. All right, so that's the 0.138. Divided by the weak acid concentration, that is the 0.081. All right, so I take that and I add, and actually I'm not putting in the 9.26 because this is 9.25527. All right, I'm going to get my final answer at the end and not round anything off until the end. So I take my 0.138 and then I divide 0.081. I get that answer. I take the log of that, and when I do, I get a pH of 9.49. All right, so again here I have more of the base, the A minus 0.138, than I have of my HA 0.081. So I knew my pH would go up slightly from my 9.26. All right, so this is a good buffer if you wanted something to be staying at a pH close to 9.26. All right, 1678. Again, it tells you buffer prepared, 525 mils. 0.5 molar formic acid. And 475 mils of 0.5 molar sodium formate. Calculate the pH. And then what would the pH be if 85 mils? Okay, so then we have a part B. All right, so first we want to find the pH. So again, MV is equal to MV. MV is equal to MV. So now we need our total volume. Well, that's easy. 525 plus 475. So that volume is 1,000. So you added, so your 525 and your 475, you have 1,000 mils total. So you got to take your 525 times 0.5 divided by 1,000. And that gives you a 0.2625. I will round it at the end. So this is a 0.2625. Again, 0.26 would be fine to put there. I'm going to leave all my numbers until the end. If I take my 475 times the 0.5 divided by 1,000, I get a 0.2375. All right, and so I have to look up the Ka for the formic acid. So formic acid, which is our weak acid HA, the Ka for that is 1.7 times 10 to the minus 4. All right, and so your pH is equal to the pKa plus the log of A minus over HA. All right, so we need to take the negative log of 1.7 times 10 to the minus 4. The negative log of 1.7 times 10 to the minus 4. And we get a 3.77. So the pKa is 3.77. So 3.77 plus the log of your A minus, all right, so your A minus is your 0.2375, over your HA, which is 0.2625. All right, and so since we have slightly more of our acid this time than our base, it's going to come down from the 3.77, but slightly because it is a buffer. All right, so plus the log 0.2375 divided by 0.2625. And that gives us a 3.73. All right, so again, this would be a good buffer for a pH of 3.77. But that was just the first part of number 78. Now it says, so part B, what would the pH be if you take 85 mils of the buffer and you're going to add 8.6 mils of 0.15 HCl. All right, so here we got to get our concentrations. So we have our A minus. We'll do HA first. We're going to have HA. We're going to have A minus. We're going to have H plus, because HCl is a strong acid. That is our H plus. All right, so our HA, we're going to take 85 mils. So we're doing MV is equal to MV. We're doing MV is equal to MV. We're doing MV is equal to MV. All right, and so our molarity of the HA in the buffer was a 0.2625. And we're taking 85 mils of that. Now we want to know what the molarity is now that we have added 8.6. So when you add 8.6 here, you get a 93.6. So we are at a total of 93.6 mils. For the A minus, we had a 0.2375. We took 85 mils of that. What is the molarity now that we're at 93.6? And then the HCl, we have a 0.15 molar with a volume of 8.6. What is the molarity now that the volume is 93.6? All right, so we got to get our three concentrations. So we take our 0.2625 times the 85 divided by the 93.6. That is a 0.2384. We take our 0.2375 times 85 divided by 93.6. The A minus concentration is 0.2157. The H plus concentration, 0.15 times 8.6 divided by 93.6, 0.0138. All right, so I just went with 4 decimals on all of those answers. Again, I round my answer at the end. So you need an equation that has HA, A minus, and H plus in it. Well, that's pretty easy because HA goes to H plus and A minus. So that's the equation that has HA, A minus, and H plus in it. And now we're going to have initial. So our initial HA, 0.2384. Initial H plus, 0.0138. Initial A minus, 0.2157. All right, so whenever you have your initials, something on the right has to be 0. If you do not have something on the right that is 0, you have to get a new initial. We do not have anything on the right that is 0. So the smaller number is going to go to 0. So minus 0.03138 minus 0.0138 plus 0.0138. And so our new initial will have a 0 for our H plus. So we take our 0.2157 and subtract our 0.0138, and we get a 0.2019. And we take our 0.2384 and we add our 0.0138, and we get our 0.2522. All right, and so now we see that we have the concentration of HA, and we have a concentration of A minus, and our concentration of H plus is 0. And so pH is equal to the pKa plus the log of A minus over HA. We already have our pKa, that was the 3.77. So you have your 3.77 plus the log of your A minus 0.2019 over your HA 0.2522. And so now you're ready to get that answer. So 3.77 plus the log of 2019 divided by 0.2522. And you have a 3.67. All right, and so what we did was we added an acid, so the pH came down. It only came down slightly because that is what a buffer does. And we will do more problems tomorrow.